I always want to try to give you applications of something like this, the ellipse. Much of algebra is pieces of a larger problem. So some of the work we've done hasn't exactly given you good applications because it's like, okay, long division, why do we need that? Well, it's a small piece of a bigger thing. But here with these conic sections, we really can start to see the applications of them just as, themselves. First, Kepler's first law of planetary motion states that the path of each planet is an ellipse with the sun at one focus. Satellites orbit around the Earth in an elliptical pattern, where the Earth is at the focus. Whispering galleries, this one I think is pretty cool. So Statuary Hall in the U.S. Capitol building is elliptical. The shape is elliptical. An ellipse has this property that if you are sitting at the focus, the reflection of that will reflect to the other focal point. So John Quincy Adams discovered that if he situated his desk at one of the focal points of the elliptical ceiling, he probably didn't know that's what he was doing, but he found this to be the case. He could easily hear the conversations near the other focal point. So you have a graph here that kind of shows that reflective pattern. It reflects to the ellipse, if you're sitting, to the other focus if you're sitting at one spot. Let's work on that idea a little bit. We know that the ceiling at Statuary Hall is 96 feet long, 23 feet tall. I'm going to graph a picture here where we can choose the center to be wherever we want. I think we want the center to be in the middle of that room. I'm just going to draw the top half of this ellipse here, where that acts like the ceiling. Obviously, the full ellipse would come down like this, but we're talking about the ceiling itself. If it's 96 feet long and 23 feet tall, this will be 23, the distance here. This distance here will be half of 96, which is 48. Because we are choosing the center to be right at the center of that ellipse, we can force it to be 0, 0. You could do that differently, but it's going to make this more complicated. That means we're going to have x squared and y squared over some numbers equal to 1 with a plus sign between them. We need to figure out what those numbers are. Under the x, remember, is the horizontal length or distance from the center out to that vertex, which is 48, and then you have to square that, right? Under the y, we do the vertical distance from the center out to the vertex. That is 23, and that has to be squared. So let's see, what are those numbers? 48 squared and 23 squared. 48 squared, 2304, 23 squared, 529. So this would be, this would be the standard form of the equation of an elliptical ceiling. Here's the interesting part about this to me, with John Quincy Adams situating his desk at the focus on the right side of the chamber. How far from the center of the major axis did Adams situate his desk? We want to know where the focus is, right? He put his desk somewhere here, wherever that focus is, so that he could hear conversations that were happening way over here at the other focus. I think that's pretty funny. So we got to find where that focus is. Remember, the biggest distance, 48 squared, is the one that's sort of by itself. 23 squared, and then, again, pick a letter, C. 48 squared we found to be 2304. 23 squared was 529. So C squared is equal to, let me do that subtraction, 1775. Square rooting that gives us an approximation of 42.13. And these are feet, right? Making sure my unit. Yep. Oh, you know what? I realized I have a typo up there. This should not be square feet long. It's just feet long. 96 feet long. 23 feet long. Okay, so where should he have his desk? 42 feet approximately from the center. That means about 6 feet from the wall. Okay, so that's one application of this. This reflective property of ellipses is pretty cool, I think. It's kind of fun to think about. I think you can actually go into this and it's like marked off now that you can stand there and your friend can stand, or your mom or whatever can stand at the other focus, and you can have a conversation. Let's talk about eccentricity of an ellipse. It is the ratio of the distance from the center to one of the foci to the distance from the center to one of the vertices. What we are talking about in your ellipse here, if this is your center, this distance we call A, out to the focus, we call that C. This E is the ratio of C to A. It's the percentage of the distance from A that, percentage of the distance from the center to A that the foci lies in decimal form. Down here are a couple of examples of that. E equals 0 would be a circle, because the foci is at the center there. So the C is 0. Something like this one has 0.23 for E, this 0.43, so that means this point is 43% of the way to here. Here it's 77% of this distance from here to here. Notice the bigger the E gets, the narrower the ellipse gets, the less circular it gets. We're going to talk a little bit more about this later, too. That wraps up our study of ellipses. Our next conic section that we are going to study, now that we have written equations of ellipses, seen applications of ellipses, graphed ellipses, our next conic section that we are going to study will be the hyperbola.